This is a joint work with Kwon, Kham, and Ryuhei Uehara from JEIST. And we're talking about cyclic shift problems on graphs. This research is inspired by some cyclic shift puzzles, which are puzzles where we have to reconfigure some tokens on a graph. So the allowed operations are shifts along some predefined cycles in the puzzles. For example, here we have to reorder these beads by just shifting along these two cycles. And there are many examples. Here is one with 4 cycles, for example, which are interconnected in complicated ways. And our goal in this research is to, given a cyclic shift puzzle and an initial configuration, determine which target configuration can be reached. And also, once we have determined that the configuration can be reached, design a practical algorithm to reach it in a small number of moves. Now, we can formalize the problem as a configuration, which is a function from a set of positions, 1 from n, to a set of colors. So each position has a token of some color. And then we have some cycles, which are part of the problem. And these are cycles from cycles on 1 to n, so cycles on the positions. And of course, a shift is a composition of this position function and the cycle we want to use for the current move. And the token shift problem asks to determine a shortest sequence from an initial configuration f0 to a final configuration ft. Previous work has studied a similar problem where allowed moves were swapping tokens along the edges of graphs. So our model can be seen as a generalization of this, where instead of just edges, we use more general cycles. Now, in the first part, we will just focus on puzzles where tokens have distinct colors. So we have n tokens of n distinct colors. And a configuration is just a permutation. It can be seen as a permutation of n items. So the positions we can reach by using our cycles are a subgroup of the symmetric group Sn. So this is a subgroup, we call it H, which is generated by the k cycles that we have. And by classical group theory, we know that this subgroup has some number of cosets, and each coset represents the configurations we can reach from a given starting position. So H is the set of position we can reach from the initial configuration, from configuration we call the identity. And then we have more configurations, which are in a space that has many copies of H, as many as the cosets of H. So let's first focus on 1 connected and 2 connected puzzles. These are the puzzle we call 1 connected and 2 connected. These are just 2 cycles which share 1 node or 2 nodes. And the generators are, of course, just 2 plus their inverses. First of all, let's consider parity. If we have if we have a cycle of ends of length L, then it's composed of L minus 1 transpositions. So if both cycles have odd length, then we can only form a subgroup of the alternating group AN, which is the group of even permutations. We cannot generate any odd permutation. Conversely, if some of the cycles, if one of the cycles has even length, then we have an odd permutation. So the subgroup we generate is not a subgroup of AN. Now, can we generate all of Sn or AN? Well, we can do it if we can form these 2 cycles. For example, if we can form the cycle of all the elements plus an inversion of consecutive elements, then we can generate all of Sn. And likewise, if we can form the cycle of all n elements plus the 3 cycle of 3 consecutive elements, then we can generate at least AN. And also we can generate them in O of n squared steps. And this is folklore, and the proof mimics the bubble sort algorithm. Now let's apply this idea to our 1 connected puzzle. Now we can prove that we can generate all of AN if both cycles have odd length and Sn otherwise. So the space is very, very big. We can generate almost all configurations in O of n square steps. We apply the previous lemma, so we can form a cycle of all n tokens by doing b to the minus 1, beta to the minus 1 alpha. And also we can form the 3 cycle of these 3 nodes by doing this transformation in red. So we have an n cycle and a 3 cycle. So we know that we can generate at least an. And if both alpha and beta are even, then it's fine. That's all we can do. Otherwise, we have an odd one, an odd permutation. In that case, we just generate the even permutation pi alpha, and then we do alpha to the minus 1 to generate any odd permutation pi. For 2 connected puzzles, we first focus on the subcase where the first cycle is a 3 cycle. So alpha is 1, 2, 3. And once again, here we can apply the same kind of idea. We have a cycle that includes all nodes except 1. And then we can construct a 3 cycle by conjugating the first one. So conjugation is an operation that preserves the cycle structure. So by conjugating the 3 cycle, we're just moving it somewhere else. Now we move it here on the nodes 2, 3, 4, so that we have this sub-puzzle in here where we can again apply our lemma and generate all even permutations here. Now to generate any permutation, including the position number 1, we first put the destination token on position number 1, and then we rearrange the rest. Now we can extend this theorem to all 2 connected puzzles, except the ones that have 2 cycles of length 4. And these we will study later. However, for the others, we have a similar theorem. So if both alpha and beta are odd of length, we can generate an, otherwise Sn, also in n square steps. Once again, we conjugate cycles. So we can conjugate beta and beta minus 1 to get these 2 cycles, red and blue. And these 2 cycles almost cancel each other. And when we compose them, we get these green ones, which are a 3 cycle plus 2 transpositions. So when we take this and we apply it twice, we just get 1 3 cycle. And so now we have 1 3 cycle. We can conjugate it, so we can rotate it by alpha. And once we have it in this position, 1 to 5, for example, then we can use it with a cycle that includes all elements except 5, which is alpha minus 1 beta. And notice that these 2 cycles, this 3 cycle in red plus the big blue cycle, form a puzzle that we already know how to solve. It's a 2 connected puzzle with a 3 cycle. So we can just apply the previous theorem here and conclude our theorem. All right, we only have the one type of puzzle to study, which is the one where the 2 cycles have length 4. So let's study it. In this puzzle, we cannot form any 2 cycle or 3 cycles, so we have to use a new idea for this puzzle. We use the concept of automorphism. An automorphism is a function from the group into itself, which preserves its structure. And conjugating by an element is an automorphism. And the automorphisms that are generated by conjugations are called inner, and they form a subgroup of the group of automorphism. Now, n equals 6 is a special case for the symmetric group Sn, because in all Sns, all the automorphisms are the inner ones. S6 is an exception. It has others. For example, this is one. This is an outer automorphism. And this is useful to us because now we can use it to study our 4-4 2-connected puzzle. We just apply this isomorphism to the 2 generators. We obtain 2 other generators that generate a subgroup that is isomorphic to our subgroup. So the 2 transform generators are the 2 cycles, 1, 3, 2, 4 and 1, 5, 2, 3, which are depicted here. And notice that they leave a token number 6 in place. So that means they can generate at most an isomorphic copy of S5. Now, can we generate all of S5? Yes, because with these two cycles, we can create these red and blue ones, like here, like we show here. And these two together form a two-connected puzzle on 1, 2, 5. And for this two-connected puzzle, we already have a solution. So indeed, we can generate all of S5. What we generate in this 4-4 two-connected puzzle is an isomorphic copy of S5, which is not a trivial one. It's an isomorphic copy of S5 that permutes all the elements from 1 to 6. It's a non-transitive copy of S5, which exists only because we are in S6. It doesn't exist in any other symmetric group. Now, let's talk about more general puzzles. We can compose our many cycles, not just two, as long as there is a subgraph of the adjacency graph of the cycles that is connected. So we look at the pairs of cycles that together form a one-connected or a two-connected puzzle, and we assume that this graph be connected and that it spans all tokens. If that's true, then we can generalize our previous theorems to puzzles of any number of cycles. However, we get a worse upper bound here on the number of steps, which is O of n to the fifth. However, the proof works by constructing a walk through all tokens by using cycles, these cycles in C prime, which are the interconnected cycles that are interconnected in the proper way. And then by using the previous theorems, we know how to generate 3 cycles on this path, on this walk W. And now by carefully composing these 3 cycles that we can generate in O of n squared, we compose them O of n cubed times, and that's how we generate every even permutation. So that amounts to O of n to the fifth. And once again, for odd permutations, we use the same trick as before. If we have an even cycle, gamma I, we just do gamma I first, and then we compose it with gamma I minus 1 pi, which is an even permutation, so we know how to do it. All right, now let's move on to puzzles where tokens may have the same color. And here we have this hardness theorem, where we're looking for the smallest number of moves from an initial configuration to a final configuration. And this problem is NP hard, even if there are only 2 colors of tokens. We reduced from the classical 3-dimensional matching, where we have 3 sets of the same size n, m, and then we have n triples of elements from the 3 sets. And we look for a subset of the triples that covers the 3 sets exactly. So it has to have size exactly m. An instance of this problem can be represented as a bipartite graph like this, and we can extend this graph to a cycle shift puzzle like this. So this is our reduction, and the final configuration is on the right. So the question is, can we go from the left configuration to the right configuration in 3n moves? All right. So if the problem, the 3DM problem, has a yes answer, then we can do it, because we just select the triplets in M, and we shift them along blue cycles like this. And so this way we can cover all of the elements in XYZ with black tokens. And now we're left with some other black tokens which we can shift along red cycles to the left, like this. And so if the 3DM instance has a yes answer, we can finish in 3m moves. And conversely, assume that we can rearrange the tokens in 3n moves. Now, the observation here is that the moves available are 3n, and the black tokens are 3n. So we need at least 1 move to get black tokens out of the yellow area. And each move must be spent to get 1 token out. For this reason, it's never a good idea to place a black token in U, because otherwise you will always have a black token, because we always want to get a black token out of the yellow area. So you will always have a black token, and U doesn't have a black token in the final configuration, so that's wrong. For the same reason, we don't want a black token in W ever. And by these two observations, now it's easy to show that the only way of going from left to right is to find a triplet that solves the 3DM instance and use them to fill the blue positions, to fill the green positions. So that's it. This is the reduction, and I'd like to summarize our results. We have studied the token shift problem in two main settings where tokens have n distinct colors, so all tokens have distinct colors. And in this setting, we characterized the reachable configurations for a large class of puzzles, and we gave algorithms to reach these configurations in a polynomial number of shifts. And then if tokens are allowed to have the same color, we show that minimizing the number of shifts is NP hard. Now, some problems that are left open for future research are, of course, improving that O of n to the fifth upper bound, which is not optimal. And then extend the analysis to more general cycle shift puzzles, also non-proper ones. Also, is the minimization problem p-space complete? And does it remain NP hard for planar graphs or graphs with a small minimum degree? And that is all. And thank you very much for your attention.